Thanks, Emmanuel, for the kind intro. I'm reminded this morning as I was looking through my slides that I gave a talk at Cornell in about 2009. So Ken would be probably the only one who would remember this. And the opening slides were very, very similar. So chalk it up to obsession, or perhaps I'm returning to things that I had set aside 7 years ago.
Just making sure we don't see any slides for the moment.
That's correct.
We don't see any slides, and the abstract was pretty much the same too, by the way, Joe.
Yeah. So, we'll see if I've learned anything in all this time. And Ken, keep me honest about that. But I think one of the things I'm going to emphasize to the students and maybe the junior faculty in this talk is that some problems take a long time, and you keep learning more. And this is one of those problems where I feel like it's been almost a career-long exercise so far, and I think it's coming to fruition. So I do believe we're on the cusp of making this stuff real, and that the community may actually also be ready to absorb some of this. So patient research is a good thing and part of the tenure process, and I'm trying to embody that today. So yes, returning to topics I was talking about in 2009. Okay, this is very similar to my setup slides in 2009, actually. It's kind of shocking. So there's this story we tell in computer science, and I think probably the leading example of the story is the Ritchie and Thompson Turing Award for Unix, that as you build new computing platforms, new programming environments arise to unlock the power of those platforms. So the mini computers, the PDP-11, were really grew when Unix and C accompanied them as a programming environment for developers. And arguably the same was true of supercomputers, personal computers, and smartphones, that programming models have arisen to try to meet the unique characteristics of these environments. But interestingly, the iPhone actually came out a year after AWS, after the public cloud was sort of invented. And we still don't really have an agreed upon programming model for distributed computing and the public cloud. And I gave this talk in 2009. It seemed like a very burning issue. And here we are all these years later, and it's still true. Okay. So I think actually this is one of the grand challenges in computer science. The fact that this has been going on this long is not merely because I'm moving slowly. Programming distributed systems is hard, and getting people to want to work on this problem is also an interesting challenge, which we can take an aside and talk about maybe. But anyway, this is kind of the problem setup. And I want to say at this point in the talk, these slides are pretty much my slides from a PAPOC keynote I gave a couple months ago, which are adapted from a POPL keynote I gave last year. And I have no particular personal interest in marching through all these slides. So I'd be much more happy to pause and have conversation with people as we go. So don't hesitate to interrupt, okay? Let's do the questions in line, in short. If you wait till the end, I'll just cover too much material and we'll miss the moment.
Okay.
Thanks. Okay, so I think this is a big deal. And, my bias all throughout, I'm a database person. This is the database seminar, so I won't pretend to call this anything else than I think the database community has something to teach the rest of computer science here, which is really about high-level declarative languages. And that the theory of these languages, as well as the practice we've seen deploying them in the SQL context, is very powerful. And so my work is going to be grounded in that theory. One of the key properties of logic languages, database theory, is that it's got a fundamentally disorderly data structure under it, which is the relation. A relation is an unordered set of tuples. Okay. One of the hardest things in distributed systems is that things can happen out of order. So it's kind of nice to take a data model that by default, its initial data structure is an unordered data structure. It's going to make easy things easy. Okay. Whereas if you think in most programming languages, the list, for example, is very basic to functional programming and it's ordered. And so if we want to start parallelizing things, we first have to undo the first basic assumption of our languages, which is that we have lists. Say, okay, but sometimes you can partition the lists or you can reorder the lists. With the relational model, we start with a disorderly data structure, which just kind of makes the easy things easy. And by the way, database systems have been parallelized and scaled since the 1980s. You know, foundational work from Dave DeWitt at Wisconsin on Gamma, from the Teradata Corporation, which started around the same time. They demonstrated that the lessons of Ted Codd on the relational calculus and algebra not only allowed us to reorganize things on disk, which is really reorganizing things in space, but also to reorganize things in time. That we can have our tuples appear at different times and be looked at different times, which is to say concurrently, and things still work out. So Codd's lessons, which were really his idea of data independence, which was about putting data anywhere you wanted on the disk, we can also put the data anywhere we want in time. All right, and it's just, it's so basic that database people almost don't think about how profound it is anymore, but it's a big deal. And so this notion of physical data independence, the idea that we shouldn't need to know where things are in space and how they're organized, is absolutely what the cloud is about, right? You know, you connect to a computer in the sky, you don't know where it is. The data that your computation is referencing might be in one of many data stores, and you don't physically know where in those data stores it is. And the platform is heterogeneous and evolving. Most recently, we also have this focus on programs that auto-scale. So when you're not using them, they scale down to 0 and they don't charge you anything. And when you're using them a little, they scale up to a few machines. And when you become the world's hottest startup, it just scales beautifully for you. So that idea of auto-scaling is physical independence in the extreme, because the timescales are very short, right? We want this scaling up and down to happen almost instantaneously. So this idea of physical independence, which is at the cornerstone of database systems, fits the cloud very beautifully as general purpose programming problem. And then I just like to say that this is, I think, really interesting work. I find it really satisfying, and it's been growing. So there's deep work across distributed systems, databases, PL, and theory, and we're asking and answering fundamental new questions. It's really, it's fun. I hope I can convince you of that today. I need to close my door just a second. Okay, I'm back. All right, so that's, the other thing, and then finally is that, I'm a database person by training, but I try not to be religious about it. So this is just a way of looking at the world. I shouldn't say this as a theorem, but I can say it as a hypothesis. I believe most of what I'm going to say today could be translated into like a functional lens, for example. I just think the database lens, first of all, it's natural to me. Second of all, because of the focus on logic and sets and things, a lot of stuff comes out very naturally, I think, in the database lens. And it certainly provides a different lens than most of the community uses. And so I think database people can add a perspective that the PL community on its own or the distributed systems community on their own wouldn't necessarily adopt and see what we see. Okay. So here's the part where I give you the talk from 2009 real fast. And so I want to share some of the lessons we learned along the way. So the prior generation of work, and this is sort of students in the early 2010s, building on the talk I gave at Cornell, which was forward-looking, is to look at language designs and see what kind of languages could we build and what could we do with them? What optimizations could we discover? What correctness conditions could we identify and prove? We applied this to things like network routing at first and declarative networking work, and then increasingly moving up the stack into like full featured sensor networks and then distributed systems. So in the middle column here, this Boom Analytics paper, we actually were rebuilding large chunks of the Hadoop infrastructure as sets of queries in a declarative language and really building a distributed system and showing the value of that. And that in turn then led to the language design around Bloom and Dedalus, which I'll talk about today, which are formally grounded languages that have the properties we really need to do the correct program analyses and the formalisms, the proofs that we wanted. So that's some of the work, but it was really language design. So we were really thinking about the abstractions. We weren't so worried with making it go fast. My last batch of students, so think the last 5 to 7 years, were much more interested in systems. So they actually discarded or set aside the languages like Bloom that we had designed and just started taking the design principles from those languages and building high performance systems bottom up. And that was mostly a matter of taste. These students wanted to be builders. They weren't interested in doing as much formal work. So this team ended up building things. Notably the ANA key value store, which I hope I'll have time to talk about, which is this wildly concurrent auto-scaling multi-tier key value store Chenggang Wu, who's the lead on this, got 2 best selected papers out of this and will be the dissertation award winner at Sigma this year. I'm super proud of his work, and he deserves all these accolades because Anna's quite an interesting system. And then on top of Anna, Chenggang and another student of mine, Vikram Srikanti, built a stateful functions as a service serverless system called Cloudburst that does some very sophisticated caching and fault tolerance on top of the Anna framework that does much more than, say, AWS Lambda can do in terms of state management. So it gives you much, much better latencies for state access than the state of the art in industry today for serverless computing. So this stack here is C++ and Python. There's no formal languages here. There's no proofs of anything, but the design principles come from all that formal work we did over the previous years. Okay, and the performance here obviously is especially with Anna, is world-beating performance. And so where I am now with my students, new batch of students, is trying to put all this together and really kind of finish the story. So 2 lenses on this. If you're going to take away anything from this talk, I recommend taking away these 2 references because they're fresh. One is looking backwards, which is the paper on the left. It was in CACM, and this is the distillation of the theory that really the most important piece of theory we got out of the work we did so far, which is this CALM Theorem, which I'll talk about today. We'll certainly go into that today. And then on the right is our forward-looking paper from CIDR last year on where this project wants to go and how we think we can build cloud programming environments today, given everything that we've learned, both at Berkeley and at lots of other places. So we review some of what the community's taught us over the last 20 years and why we think now is the time to deliver essentially LLVM for the cloud, right? What is going to be the compiler toolkit for the cloud? We think over the next 5 years, that's a very plausible agenda. So these 2 papers, I think, are a distillation of kind of where we've been and where we're going. Okay, so, and I said this at PAPOC too, is this really a database seminar talk? It sounds like some kind of PL talk, and I know you guys have lots of PL at Cornell because I've inherited at least one of your postdocs. And I get on phone calls with Andrew Myers, but mostly today, I will be talking about consistency of entire applications. So that really is general purpose programming for the cloud. And that is really the target application. Now, I'm going to use database ideas here. And I think as database folks in the room, we should be ambitious about the applicability of our ideas. So why not apply our ideas to all of computer science? But still, there's going to be some lessons here for database research. So you might ask, like, if you're talking about entire applications and all I'm interested in is databases, can you tell me anything about like transactions, reads and writes, general purpose data stores? And, is this going to be one of these talks where like the database audience actually isn't going to be interested? It's a fair question. I mean, this talk doesn't sound like a database talk, and that hurts me a little bit. But trust me, I am a database person. There will be plenty of database goodness along the way. And if we get to the Anna stuff, we'll actually look at a database implementation using these ideas. Okay. So with that, that's the end of the intro. What I want to do now is the talk has 4 parts. I would guess we can cover 3 of them, honestly. Whether we get to the 4th one or not, I'm not sure, but it's short. So I want to start talking about declarative programming. What did we learn over 15 years? And why did we come to this idea that we needed a new kind of theory for this? So that's going to be the motivation. And then we'll talk about some of that theory and then talk about some of the systems that we built over the last 5 to 7 years. If time permits, I'll talk about some of the going forward work as well. Okay. This slide was almost exactly shown in 2009, but I used Datalog. Today, I'm going to use SQL. But this is just to get you in the mood. You might think of routing on the internet, finding routes on the internet or in a network as querying. And this was the earliest work we did in our research group, was to say, hey, all these network protocols feel like they're just transitive closures on a graph. I learned that transitive closures on a graph are 2 lines of data log in graduate school. And indeed they are. I wrote them in SQL, which is maybe 10 lines instead of 2, but it's a pretty simple thing to declare a transitive closure. You say, I'm going to have a table of links. Okay. And then I'm going to have this one recursive query that's going to compute paths from links. And here's how it works. So we start with our links table of individual edges between nodes. And then we say paths are links. So everything in the link table is in the path table. So the paths are green, the links are yellow. So there's all these paths of length 1, which are just the links. Union, and this is the inductive case, right? If you have a link and you have a path, you can prepend the link to the path to make a longer path, right? So you take your links, you join your paths, or you take your paths, you join them with links, and you get longer paths. And so you iterate this thing, you get longer and longer paths, and eventually you find all the paths, right? And that's pretty straightforward. It doesn't seem like it has a lot to do with how TCP or BGP or one of these protocols works. TCP is not a routing protocol, sorry. Various routing protocols work. Doesn't feel like this somehow. But you can add to this a little bit so you can get things. So that's, by the way, a link. We can ask questions like, find me all the paths from a particular place, or you can actually extend this gently to find me all the cheapest paths from a particular place. So find me the shortest paths from any single source shortest paths, classic graph algorithm, okay? So you can express all this stuff. The cool thing is that under the covers, a query optimizer chooses the actual protocol. It chooses the actual algorithm. And so what we discovered when we sort of played with this idea and built it was that you could write this stuff in Datalog or SQL, and then you could apply very traditional query optimizations like join ordering. And depending on the join order, you would get different network protocols from the literature. So one protocol you might get is the distance vector protocol, which is used in BGP and other internet settings. But if you reordered the terms, you would get dynamic source routing, which is typically used in cellular or wireless settings. And it was just like, wow, maybe really we shouldn't be inventing protocols. Maybe what we should be doing is specifying desires declaratively and letting an optimizer figure out what's going on in the network and what would be the best way to implement these protocols. If nothing else, this work showed there's a strong connection between database query optimization and protocol design, which is pretty surprising and sort of opens up opportunity. Okay, so this is 2006 stuff. The CALM version is from 2009. We were pretty excited about that. So we decided to move up the stack and build more complex algorithms and distributed data structures. So the one we went after, because it was a super hot topic in the 2000s, was this idea of distributed hash tables as an overlay network. So imagine you have a whole bunch of computers, maybe they're browsers that people sign into and sign out of. So they may not stay up for very long. Right? And this was in the context of peer-to-peer computing. So they were computers that people would turn off. They were like personal PCs. And you want to build a distributed hash table on them. So you want keys to live in the network, but the keys are going to move around as nodes come and go. And they'll need to be replicated for fault tolerance because nodes come and go. But they'll also, the routing of where is key number 4 is going to change over time because computers are going to come and go. And the set of replicas that hold the value 4 will change over time. So there was a dozen of these kind of overlay distributed hash table protocols designed in the early 2000s. And they were idiosyncratically different from each other, but it sort of, from 1,000 feet, you kind of didn't care. It was just a distributed hash table. So again, it felt like an opportunity for a place where a declarative language would allow us to explore this space more systematically as a set of optimizations. So our first challenge then was to be able to show we could easily build one of these distributed hash tables in a declarative language. So we actually built a fairly high performance C++ runtime for one of our languages, which we called Overlog. And we targeted it specifically at building these overlays. So it was all about networking and low latency messaging. And over it, we built one of the leading distributed hash tables, MIT's Chord hash table. And this is it. This is the implementation of Chord in Overlog, which is a Datalog variant. And I don't expect you to be able to read this. But one thing I do expect you to be able to imagine is you can print this piece of paper and you can take it to the coffee shop and Joe could explain it to you in the course of half an hour to an hour. I could walk you through the code. We take it one at a time. How do lookups work? Well, there are only 3 rules. Let's talk about lookups. Okay, what happens when nodes leave? That's churn handling. Well, we'll talk about that. So I could talk you through this in a sitting. The MIT C++ implementation is 10,000 lines of C++. And I cannot talk you through that in an hour, right? So there's a qualitative difference here in terms of moving up the stack, just of explainability. And, I can't quantify that exactly, but it's something around when you get 2 orders of magnitude less code, things do become easier to understand. This is also, a more formal language. In principle, we could prove things about it. In practice, we never did with this particular language. And we'll go on and talk about why in a minute. So the next thing we did moving up the stack was to build the internals of Hadoop, which is this paper Boom Analytics. And here the goal was, first of all, to write the entire file system, which was the Google file system cloned as HDFS. We rewrote it as BoomFS entirely in Overlog. And we had a Java implementation of Overlog for this because the whole Hadoop stack was in Java. Among other things we had to do, we had to implement Paxos as part of this, and it turned out to be fairly nice. So this was our first classical distributed systems protocol. And the basic implementation of Paxos was 22 lines, or 22 rules, I should say, 53 lines. What was cool about it was that almost every single line corresponded to a sentence in Lamport's original paper. And that may be a little bit about Leslie Lamport, that he thinks in logic statements. But it might also be that the way a logic statement is written, right? It's precondition, postcondition, yeah? And that's a lot like the way message handlers are written in a protocol. If I receive a message, then I know a thing. So there is sort of a domain fit between the use of logic and protocol design. At least that was something we observed when we were doing this. And so with all that background then, here's some things that worked well in the Boom Analytics stuff, which was our most mature, full-featured piece of software that we wrote in this style. First, it was, again, much smaller than Java, maybe 10 to 20 times more concise. And the performance in this case was competitive. I will say that Hadoop was never a fast system. It's just kind of a low bar. But we didn't bother tuning much because neither did the Hadoop people. If they were tuning more, we would have tuned more. I mean, I think you can hit a performance goal with a distributed system in this environment. We had a nice separation of policy and mechanism because a lot of the mechanism things were underneath the first order declarative stuff, so we could kind of play with that. But more importantly, we had this ease of evolution. So in the paper, we talk about how we took the initial design of HDFS and extended it in a set of ways. The first thing we did is the HDFS of that time had a single master. And so if that master failed, the whole system would go down. We're not supposed to say master anymore, so single central node coordinator. So if the coordinator fails, the whole system goes down. So we added failover and Paxos to the coordinator to show that it would be pretty easy to build a replicated coordinator that was fault tolerant. And again, writing Paxos in our language wasn't that scary. Now today, there's lots of Paxos libraries available. At that time, there weren't, so you'd kind of have to write one almost by hand. The second thing we did was we showed that coordinator node, it keeps the metadata of the entire file system. At some point, it needs to scale out. At some point, it doesn't fit on a single computer. And the Google file system people had written about this. And the HDFS community, the Hadoop community, had run into this problem where you keep having to buy a bigger and bigger coordinator node to run the system. And so we showed how easy it would be to scale up our code just simply by hash partitioning all the tables. So all of the state in our implementation, everything about the file system was in relational tables and was queried with relational queries. We all know how to partition or shard a relational database. It's totally straightforward. And indeed, causing the coordinator node to scale was the work of one day. And it was done by a person who wasn't even in our group. Rusty Sears, who's one of Eric Brewer's students, wanted to play with us. And he took the time to learn Overlog and do this, and the whole thing took him a day. So it's really that simple. Another thing that came out really nicely is if everything is queries, and database folks in the room, you understand this, right? If everything's queries, then everything gets compiled down to query plans, right? And in query plans, there's this very explicit data flow, and you can interpose sort of monitoring anywhere you want in that data flow. You can sort of listen to any edge in the data flow of the system simply by rewriting the queries, right? You take the thing that's below that edge, you call it its own view, and then you put a name to it, and that's your monitoring query. So it's super easy to interpose monitoring everywhere in the system. And that idea of simple interposition is really quite powerful when you think about building systems. So these were all things we felt were positive lessons. Now, not all the lessons were positive. And so here's the part where we had to be quite honest. The semantics of this Overlog language we had were not well specified. We didn't even know this at the time, but it turned out that the language wouldn't quite work. Very much like Prolog, which is the granddaddy of Datalog. If you understand how the interpreter is working, you understand the language. So there's only an operational semantics, and that's not good. Datalog's an improvement on Prolog because it has a formal model theoretic semantics. It has a meaning independent of execution. In fact, there's many ways to execute a Datalog program that will give you the same answer. And overlog, we went back to the original sin, and our interpreter was part of the semantics of the system. When programs would break, we would do the thing you do in this world, which is you change the language. So you change the execution engine so that your program doesn't break anymore. But of course, the side effect of that is some other program breaks, right? Because you just haven't thought through everything. And so what we found, the particular thing we found, the kind of pair of things that would cause bugs was if there was state update or change in the state of the system, and there was uncertainty, particularly around race conditions, timing of messages, interleaving of activity. Those two things together, as you would expect, would cause semantic woes. And so we had to step back and ask ourselves, what is this language supposed to be? And, what did we get wrong at that time? It's kind of embarrassing. And again, all the folks in the room who are database folks, I should have known better, and we should all take a lesson from this. When you apply database lessons to things, you can't forget your databases. So when we were working on routing, we said, hey, all you need is data log. That's great. And so you just have like this virtual database in the sky that represents the links and the edges, and everything's good. But really, that's not what you have. What you have in the sky is a bunch of little databases, one on every node, and they send each other messages, right? We know what this is called. This is a distributed database. And when you start talking about distributed databases, you have to start talking about distributed transactions or something distributed around update semantics. And so we need to talk about consistency. And our languages did not talk about consistency. Right. And that's this issue of change in timing, right? It's concurrency control. So shame on us for not thinking about that. And in retrospect, it's a little weird that we didn't think of it earlier. And so, I'm not the world's best database researcher, but I'm not a complete fool. And somehow I had fooled myself for a bunch of years that I didn't need to think about transactions. That should be interesting, at least to me. It should spark my interest. And so put that thought on the shelf for a minute. How was it that Joe forgot transactions for a few years? What was going on in his head? All right, well, let's talk about how we fix this. We know how to fix this, right? There's a bunch of Turing Award winners told us how to fix this. So Leslie Lamport won the Turing Award in large part for his work on consensus. People like Ken have done foundational work in this area. There's all these thought leaders and sort of early generation computer scientists have taught us this already. Consensus, just to remind you, at Cornell, I hardly need to. Simple consensus is to get a fixed set of machines to choose to do the same thing or to choose the same thing. And then state machine replication is the generalization where you get a fixed set of machines to choose the same sequence of things, right? So Paxos and multi-Paxos have become sort of the Vaseline and Band-Aid brand names for these tasks, yeah? And then in databases, we have commit protocols like two-phase commit. Jim Gray won the Turing Award for transactions, though he didn't, in fact, invent two-phase commit nor ever claim to. But I'll put his picture on the slide just so you get the impression that, like, these people are, well, certainly a generation before me, they were my mentors and I missed it. So there they are. Shame on me. But this is tricky stuff, right? And particularly, the consensus stuff, the kinds of things that you work on, Ken, it's hard. And every time I try to teach this stuff, I have to go back to the book and make sure I really have my P's and Q's before I go to the board and teach this to students. And, tricky stuff is important. This is the kind of tricky stuff, though, that's actually you don't want to use it. So it's hard and confusing, but also it's bad. So what am I talking about? Why am I being a jerk? Well, don't blame it on me. This is actually the words of Ken Berman, transcribing something James Hamilton said, I believe, in Ithaca at a workshop. I love this. And I don't know if James actually said this, Ken, or if this is your wording, but it's just beautiful. It's like poetry. It's distributed systems poetry on coordination avoidance. So I like to read this out loud. The first principle of successful scalability is to batter the consistency mechanisms down to a minimum, make it as hard as possible for application developers to get permission to use them. Or the way I like to say it, thank you for all the Paxos, Dr. Lamport, but we don't want it anymore. So we really want developers to avoid using this stuff. Why? Well, imagine that you have an intricate stack of stuff in the cloud, and some junior developer decided to put a little bit of a consensus protocol somewhere deep down inside. And that consensus protocol requires a quorum, right? And let's say that there's some network partitioning and failures, and it doesn't get that quorum. Well, what happens? It waits. And then anything that depends on that component also waits. And suddenly you've got the whole data center going down and you don't know why. And eventually you find out, oh, geez, there was some Paxos somewhere that was in a critical path place and it was not fault tolerant. So the whole, the whole assembly just kind of came down. Okay. And so wise folks don't let just anybody put these consensus protocols, these kind of waiting coordination protocols in the middle of stuff. All right. So takeaways from our experience in the past. Interestingly, I was fooling myself for all these years, but it was okay. We didn't need coordination when we were doing the network routing stuff. It just didn't come up. It didn't matter. Sort of in the spirit of James Hamilton. We didn't reach for distributed transactions or consensus, and it was cool. But when we started doing some of these distributed hash tables, they had races in them somehow. They were racy. And we felt like we did need coordination finally. And in fact, for BoomFS, we implemented coordination. We implemented it in the languages that we had developed without coordination. So at some level, we had a low enough level language we could implement coordination. The question was, when did we need it? Somehow we didn't need it for network routing. We did need it for these overlays. What is going on? When must we coordinate? And maybe we can implement that coordination in one of these declarative languages, that's fine. But the real question, the foundational question is, when must we coordinate? And when are there ways where a smart programmer can avoid coordinating? Okay, this is a theory question. So let me, the big question is like, what is coordination really for? And weirdly enough, you go look at the papers and you go to talks about them, and it starts with the assumption that you have something that you need to form consensus on, or you have a transaction you need to commit. And if you ask, why do those things exist? It's like, well, concurrency is hard and you can get race conditions. Okay, but in network routing, I didn't get race conditions. Actually, in building the Hadoop file system, must I have race conditions? Is there a version of the Hadoop file system I could build that would have no race conditions and wouldn't need coordination? I don't even know how to ask and answer that question at the time we're doing this work. Right? Race conditions are circumstantial. They're a thing that happened because of the way you wrote their code, but are they necessary? What is coordination fundamentally for as an expressive piece of a computational model? So this leads us to the logic foundations and to the questions we really wanted to ask. Any questions before I go on? Let's take a pause.
Are there any questions in the room or online? If so, then just unmute. Maybe while the others are sick. Oh, yes, please.
When you say you need when you need consistency or not, do you include like serializability is consistency?
Great question. So serializability, does it require a coordination protocol or not? Is there a way to build, I don't know, some multi-version transactioning scheme maybe that has no coordination in it and get serializable schedules out of it?
I don't know. That's what I'm asking.
I know, right? It's like not obvious that the answer is, of course not, Joe, because blah.
I mean, the reason I'm asking partially is because in the work Natasha and I were doing, what we're trying to do exactly is avoid strong coordination. I don't actually need Paxos to get serializability, but I'm doing some sort of coordination. I'm doing concurrency control. I have quorums. I don't need my replicas to be consistent. I don't need them to be totally ordered, but I'm still querying and I'm waiting for quorums in order to guarantee consistency. So that seems to be like a step towards what you're saying, but it's not coordination free, I would call it.
Well, and you're exactly in the soup, right? You're like, I can't figure out a way to make this coordination free. It feels like it probably couldn't be coordination free. Otherwise you wouldn't be building what you're building, right? Yeah. But it'd be nice if somebody was to assure you that the path you're going down is reasonable, right? There is no coordination-free implementation. It would be nice to know that. Right. So, spoiler alert, serializability not be done without coordination. It requires it. So that's good. So you're absolutely doing the right thing. But I love the fact that the question's not obvious, because that's exactly the point. It's like, what properties of programs require coordination? And the simplest ones we can think of as database people are the things we use coordination for, right? We use coordination for serializability. So surely we're not nuts, right? We need it, right? Do we? I don't know. And so that's the kind of thing we want to be able to prove for ourselves. And then more generally, if you think of this as like complexity theory class or logic class, if I give you a construct that gives you coordination, how have I expanded the power of your language? If I take that construct away from you, what programs can you say and what programs can you not say? So that's the kind of question we wanted to ask, right? And that's where we're going next in the talk.
Cool. Any other questions for the moment? Perhaps
I hope I made clear that like we totally tripped across this through this weird path of network routing where somehow we didn't need all this coordination that I'd been taught over all these years. It's like I was dreaming for a few years in this land of coordination freeness. And then the dream died. I didn't know why. So sometimes you trip across these things if you're patient for a while and you explore down a path and you go to the end of the path and you fall off the cliff. That's interesting. Great. So try to give folks a little bit perspective on exploratory research here. Not all research, not all results have to be positive. Sometimes you get negative results. You go, oh, that was interesting. Kind of hurt, but it was interesting. Okay. So my suspicion, based on where we are in the talk, is that we will not get very much further. So let's talk about this question, and probably we'll wrap up. So we needed a better language to be able to answer these questions, because this weird language we had, Overlog, with its weird interpreter-based semantics was no good. So we came up with a much cleaner language. This is really the work of Peter Alvaro, called Dedalus, and Dedalus is a formal, model theoretically grounded variant of Datalog that captures time, space, and asynchrony in a well-founded kind of way. I don't mean well-founded in the negation sense. I mean well-founded in like it's got a good foundation. And so this was done in a declarative language. It's got a clean model theoretic semantics, and you can, as with all Datalog programs, you can implement it as data flow, so you can turn it into a bunch of query plans. Okay, and so the Dedalus paper actually has been pretty influential, even though it was in a tiny little workshop, but a bunch of theory work that followed uses it as the frame for proving things. Bloom is a sort of pragmatic and souped up version of Dedalus where we added, it runs for one thing in Ruby, and we added support for CRDT like lattices, if you know what they are, to our language. And so it's got some interesting combination of lattices and logic, which I won't get time to talk about today. Now the question is, how can these languages help us decide what we were just talking about when we need coordination? How can anything help us decide? So let's return to that question of what is coordination for. And in the spirit of theory, let's get on the whiteboard, so to speak. Suppose you understood everything about your program. So not just what its reads and writes were, you actually understood the entire semantics of the program. You knew exactly what it was going to do with the data, with its state. Which of those programs have a coordination-free implementation? So you know the program spec, you know its semantics, you just want an implementation that's coordination-free. Some programs have that, and we'll put them in a green circle. And then there are programs that require coordination, and those are the other programs, right? They're outside the green circle. They're all the other programs. So there's this blue circle of all programs with this green circle of coordination-free programs in the middle. And I want to know what this green line is. And this is a question of computability. Okay, I want to know which programs are inside the green circle, which programs are out, and what is the test, right? The test is that green line. So my conjecture in a keynote at Pods in 2010 was that the test is monotonicity. And then this is what we call the CALM conjecture. Consistency is logical monotonicity. A distributed program P has a consistent coordination-free distributed implementation if and only if it is a monotone program. So it turns out the if case is easy. Take a monotone Datalog program, and of course it's coordination-free. It's like you just keep kind of deriving facts, and those facts can be derived in any order. So you can derive them by sending messages over networks, and the network can reorder things, and you get a consistent answer at the end. So the if direction is trivial. The only if direction is weird. And in fact, I wasn't able to prove it at the time. That's why it's a conjecture. Okay. Within a year, though, Tom Ameloot and his advisors at UHasselt in Belgium had turned this into a theorem. And of course, the key to any logic theorem is like definitions. So they had to have careful definitions of consistency and coordination in order to really nail this down. And I was playing fast and loose in the keynote talk, of course. And so this is a very beautiful paper, and there's follow-ons to it that are also very, very interesting. So if you're interested in database theory or distributed systems theory or programming language theory, I recommend this paper. I think it's really, really cool. Let me briefly give you a proof sketch of how they do this, mostly by definition, because that's the key part is the definitions. So first, what's the definition of consistency? I want something like eventual consistency, but I need it defined for my program semantics, not just for my data. And the idea there is basically confluence. I want it to be the case that no matter what order the messages come in, once they all arrive, any order of the messages will result in the same program outcomes, which is to say that the program is a deterministic function from an input set of messages to an output set of results. And because they're sets, they're reorderable, right? So there's non-determinism is allowed in the message ordering and in duplication and all that stuff. So that's what we'll define as consistency. Okay. The outcome is independent of the non-deterministic shenanigans of the network. Sorry. And Amalut and company adopt a particular computational model called a relational transducer network, where every node in the system is kind of like an actor. They get in data, then they run queries on the data, which are relational queries in a language like Dedalus, and then they send data on the output. And the Dedalus model and the relational transducer network model are very similar, actually, which I won't have time to talk about today, but they're really very similar. One of the cool things about their model here is the query language is pluggable. So you can talk about if I give you a more or less powerful query language, I can compute more or fewer things in this transducer network. So it's a bit like a distributed computational model over query languages, over declarative languages. Monotonicity is the straightforward definition. If you have two input sets, S and T, if S is contained in T, then the program output of S should be contained in the program output of T. As the input grows, the output grows. So that's the definition of monotonicity in a set-oriented context, right? That's the logical monotonicity. We mean set-wise monotonicity. The cool thing, and this is answering the question, why is Dedalus a nice language for this, is relational languages have a simple syntactic check. It's conservative, but it's pretty powerful for monotonicity, which is like take first-order logic. If you have existential quantifiers only, it's monotone. If you have universal quantifiers or negation on existential quantifiers, same thing, it's non-monotone. So you can just look around in the syntax of your program and you can say, yep, this is a monotone program, or smells non-monotone because you're using for all. Now, sometimes you can take programs that have for all and rewrite them. So it's a conservative check, but it's an easy one. And relational algebra, if you're writing things as data as query plans, same deal, cross product, select, project, join, those are all monotone. Set difference is non-monotone, right? And that's it. That's the whole relational algebra. So these languages make monotonicity very easy to find, which is great. Trying to find monotonicity in a Java program is misery because every time you update a variable, it's non-monotone, which means you have to think about, well, suppose I didn't update the variable. Suppose I versioned the variable in array and always looked at the right end of the array. You have to start thinking about program transformations to try to figure out if your Java program is indeed monotonic. But you're not going to get it from the syntax. It's going to be a deep analysis. It's not going to be a simple syntactic check. So these languages, these logic languages are very nice for getting first cut monotonicity checks. And then we need a definition for coordination. And this is where I think the really deep insight from Amalut and company comes. And here's the idea. In a distributed system, we're going to send messages. It's a distributed system. Some of those messages are kind of for computing the answer. Some of those messages are for coordination. Which ones are which? And this would be like, in a lot of cases, this would be a good place to stop the class and have people raise hands. Time's a little short, so I'm not going to do that. But, if I'm running a distributed system, which messages count as coordination messages if I don't actually know the code? And which messages count as real messages, Okay, so what they came up with was very clever. They said, look, imagine that we take the state of our program and we think about all possible ways of sharding that state at the beginning of the program. One of the ways you could shard the state, for example, is all the states on a single node. Now, that kind of feels like cheating, but think about, we're going to look at the space of all possible partitionings. That is one of them, right? all the states at node 1. And we'll say a distributed program uses coordination if it requires messages that to be sent under all partitionings, including the one where all the states are already in one place. The messages you have to send no matter where the data is are coordination messages. Concrete example, if you're asking, is there no 5 in the network? Can I assert that nobody has the value 5? If you don't know how the data is partitioned, even if you have all the data, you still have to ask everyone, do you have a 5? Do you have a 5? Do you have a 5? And everybody's going to say no because they don't have anything. But I don't know that, right? That's an example of coordination. And you can see how not exists, how non-monotone questions kind of fit. But anyway, this is their definition of coordination. It's just definitional. And then they go on to prove that you only need this coordination if your program is non-monotone. Otherwise, you don't need the coordination. So they have the bidirectional proof based on these definitions. So 2 canonical examples. The first one, and these are classic distributed systems examples. They're almost the same program. The first one's distributed deadlock detection. Every distributed database has it. And the way it works is you have a weights for graph that's partitioned somehow across machines, right? And it depends on where data resides and where locks get set and blah, blah, blah. But the point is this graph gets generated. So machine 1 might have an edge between 2 transactions. Machine 2 might have 2 edges. Machine 3 might have a 4th edge. And the way that you compute deadlocks is they start gossiping essentially their edge sets to each other. And so here, if machine 1 sends a message to machine 2 with its edge, machine 2 can say, haha, I see a cycle between T1 and T3. And it could autonomously, machine 2 all by itself could declare deadlock at that moment, the minute it hears from machine 1. It does not have to consult with machine 3. It does not have to ask machine 3, do you have anything that could contradict this cycle? Because it can't have anything that can contradict this cycle. That's not how cycles work, right? Once you have a cycle, more edges does not change the result, right? So cycles are monotonic. And once you find one, you can report that you have a cycle. Totally monotone program. Here's another one, distributed object garbage collection. So you have a root node and it points to objects and the objects have sub-objects and the objects are distributed across multiple machines. Lots of distributed programming models are built this way, especially in the 80s and 90s. And we want to ask the question, is there a disconnected subgraph from root, right? So by inspection, because we have a bird's eye view, 05 and 06 are disconnected. But the thing is, if machine 1 talks to machine 2, and it says, haha, I see there's a path from root to 01 to 03. Machine 2 knows there's a path to 03. It can mark 03 as safe. But can machine 2 mark 05, 06 as disconnected? No, because it's quite possible that machine 3 has a connection from root to 05, right? We don't know. And here, information that would come later might change your hypothesis, right? Machine 2, when it hears from machine 1, might think 05 and 06 are still disconnected. But machine 3 might counter that hypothesis, right? It will change what you think. So suspecting garbage is not enough. More information can change the result. So you're required to check all nodes under any assignment of the objects and nodes, even if all the nodes were in one place. All right, and look at this syntax. Here's English. The first one's an existential query. The second one is a negated existential query. It's so obvious that one is monotone and one is non-monotone. It's like in the English, right? So this is how we want to program so that we can analyze for this stuff. And it also illustrates how natural the CALM conjecture really is. Okay, so a bunch has been written on this. The easiest read is this CACM paper from September 20, which has this proof sketch in it. Yeah, there's more to the story. There's a whole bunch of other hypotheses that I had in that keynote talk, and some of them are technically not true, but sort of true, and some of them are false, and some of them are true. So Tom Amalut has a nice survey paper from about 2014 of the state of the research at that time, and we go over some of the open questions now. And I'm still working on this stuff with folks in the theory community. Dan Susiu and my student Connor Power and myself are digging in deeper in this space. Okay. We got a couple more slides and then I think I'm going to stop. So a couple of frequently asked questions. A common misconception is that I'm trying to say you should write only monotone programs. And I'm not saying that at all. In fact, the languages we designed provide both monotone and non-monotone constructs. The key is that they have a linter that tells you that if you're using a non-monotone construct, you're using it wisely. Or if you're not using coordination where you need to, here's where you should add the coordination to protect your non-monotone construct, right? And they make non-monotonicity a less natural thing to reach for, which is a good thing. So if you're programming in a language like Bloom and Dedalus, you're much more likely to write select, project, join than you are to write set difference, so to speak, right? So that's a good thing. So in a distributed world, we want languages that discourage people from doing stuff that requires coordination. So you want your language's default kind of syntax and default constructs to be monotone. And by contrast, most languages make state mutation and sequential statements the most natural things, and they are directly the things that are non-monotone, and you have to undo them to do any analysis. Okay. FAQ number 2, monotonicity. That doesn't cover very much, right? Actually, most programs are not monotonic, but most programs are mostly monotonic. And it turns out even coordination protocols, even Paxos is almost all monotonic. And Michael Whitaker sort of tripped across this in his thesis work with me. Michael's a Cornell alum, super smart guy. And he was working on trying to make Paxos scale up and be more higher throughput. And all the tricks he employed were simple things about replication and partitioning, simple database query processing scaling tricks. And the reason they worked is that if you unpack multi-Paxos enough, you find tons of things that are trivially monotonic and therefore trivially replicable and trivially partitionable as well. And so our next challenge, David Chu, another Cornell alum, also a really smart guy who's working with me, so I'm very grateful to your pipeline, is working on auto Whitaker, essentially. So trying to take Michael's work and turn it into compiler optimizations, where we can take protocols, maybe Ken has a new protocol that's really cool, and we can figure out where in that protocol we can systematically apply parallelism and replication to scale things up. Now, a tricky bit with all this is if you have non-monotonicity, so you need coordination, is there a way to get it off the fast path? So somehow you're doing it in the background, or you're doing so little of it, maybe all you have is a counter that's just increasing. And that counter can be on one machine because it has to be coordinated. So we'll just run no replicas of it. We'll run on one machine, but it can go so fast because all it's doing is incrementing a counter that it can keep up with hundreds of other machines doing high throughput monotone things. So this challenge of like, how do you move the non-monotonicity into the background or into a very small place? That's part of I think what compiler optimization needs to look like in distributed systems. Okay, so takeaways. CALM, monotonicity is the necessary and sufficient condition for eventual consistency. Right, this is that bright line we wanted for what can you do without coordination. If your problem is monotonic, it should not need coordination, and you should try to stay in that category wherever you can. If you're using coordination, be sure your problem is inherently non-monotonic. Dedalus is a nice, clean language for distributed programs rooted in data log. If you're doing formal work, it's a language you probably want to look at. Bloom is an example of a practical language with Dedalus semantics. It looks kind of like Spark or Pandas, compiles down to data flow. So you could imagine this becoming real. And that would be what some of the rest of the talk would be about. It would be, how do you make all this real? But I have consumed 55 whole minutes and taken a few questions. So I'm going to stop here halfway through the talk. There is an hour-long race version of this talk where you can hear me yammer through the slides really fast on the internet somewhere.